Hi everyone, welcome to Calculus Lesson 3.4, Limits at Infinity and Horizontal Asymptotes. So yes, I know we've been doing derivatives for so long and now we're going back to limits, but don't worry, you just practice limits for your midterm. So they should be relatively fresh in your mind. Now, for limits at infinity, let's look at what it is and how it's actually related to those horizontal asymptotes. So a limit at infinity is really, we're looking at what happens as x approaches positive or negative infinity. So that means as the graph goes further and further to the right, is it approaching a specific value? As x goes further and further to the left, is x approaching a specific value? This is how we would write it. Limit as x approaches infinity, or limit as x approaches negative infinity. So we're just looking at what happens to the graph as it goes further to the right or further to the left. Now, how are they related to horizontal asymptotes? Well, if there is a horizontal asymptote, then the limit at infinity generally will be approaching one of those asymptotes. Okay, so let's take a look at an example and see if I can clarify that for you. Okay, in this case, it said find the limit, infinite limits, and limits at infinity of and asymptotes for the function f whose graph is shown. So notice, as I go further and further to the right, this graph is approaching positive 4. So my limit as x approaches positive infinity is positive 4. Okay, so I took care of this asymptote and I wrote it like this. The limit as x approaches infinity, f of x equals 4. Next, I'm going to look at what's going on as I go further and further to the left. And notice that it's approaching positive 2. So that's another limit as at infinity. Okay, so this is how I wrote it. Now the next thing I notice is that I do have some infinite limits right here. At negative 1, as it approaches negative 1 from the negative side, it's going to positive infinity. As it approaches negative 1 from the positive side, it's also going to positive infinity. Okay, so I'm going to write that one next. Now, because both of those matched, I could just write a single limit because they match the same type of infinity. So I can just write it like this. Now, the last thing I notice is that as it approaches positive 2, it goes down on this side and up on this side. So I can write two separate limits for that. Okay, and those are my infinite limits. Okay, so these are my infinite limits. I did 2 from the negative side is negative infinity, and 2 from the positive side is positive infinity. Now the final thing I have to do is identify all of the asymptotes. We have 2 vertical asymptotes, one at negative 1 and one at positive 2. We also have 2 negative asymptotes, one at 2 and one at 4. So I need to identify all of those. Okay, and this is my final answer. So all of this is what they asked for. These are my limits at infinity, these top 2. Then I have infinite limits for these next 3. I have my vertical asymptotes and my horizontal asymptotes. Okay, let's look at another example. In example 2, it asks me to find these 2 limits. As x approaches positive infinity, find the limit of 1 over x, and the limit as x approaches negative infinity of 1 over x. So what I'm going to do is I'm going to bring up a graph of this function because that will make it more obvious what these answers are. Okay, so notice what's happening. As x approaches positive infinity, this function is approaching the x-axis. It's approaching 0. And as x approaches negative infinity, it is also approaching 0. So let me show you what this is, and then I'll explain what this means in terms of asymptotes. Okay, so what happens here is that as x approaches positive infinity, we get 0. As x approaches negative infinity, we get 0. This means that 0 is a horizontal asymptote of this function, which we kind of already knew from our Algebra 2 and our pre-calculus. Now let's take a look at rational functions. As you know, rational functions tend to have asymptotes, both vertical and horizontal. So here are some shortcuts to figuring out what their values would be when we're doing limits at infinity. If the leading terms have the same power, you just divide their leading coefficients. Okay, so if they're the same power, you just divide the leading coefficients, and that is the value of the limit at infinity. If the denominator has the greater power, the limit will be 0. So if you have like x over x squared, the limit's going to be 0. And if the numerator has the greater power, you're either going to have positive or negative infinity as your limit, and you'd have to investigate what that would be. So let's take a look at a few examples. In example 3, it wants us to evaluate the limit as x approaches infinity of this function. Now notice, we have equal exponents. That means that I just do 3 over 5, and that is my answer. So my limit is 3/5. In example 4, they want you to find the horizontal and vertical asymptotes of the graph of the function f of x equals the square root of 2x squared plus 1 all over 3x minus 5. Now, to find the horizontal asymptotes, I really just need to find the limit at infinity of this, so at positive and negative infinity. Now, please notice that there is a square root in this numerator. Okay, and what that's going to do when you do the square root of an x squared, now normally we can't separate this because of this plus sign here, but we're just looking at degrees right now. Looking at the degree, this is going to be 2x squared to the 1/2 power. Now, if you simplify that, you just get 2x. So really, this is going to be the square root of 2x over 3x. Okay, let me show you what that would look like. So notice it looks like this. These x's have the same exponent, which means that for my horizontal asymptote, I just do the square root of 2 over 3. And that is the horizontal asymptote. Okay, but remember, we did a square root. There should be a plus or minus sign right here. So technically, we have two horizontal asymptotes, one at the positive value, one at the negative value. So for my horizontal asymptotes, I have plus or minus square root 2 over 3. Next, I need the vertical asymptotes. And remember, those usually occur at the zeros of the denominator. So I just have to set this equal to 0 and solve for x. Okay, so my vertical asymptote is 5/3. Now, if they had asked you to find the limits as it approaches this vertical asymptote, we would need to investigate those separately. Okay, so we weren't asked to investigate that, so I'm not going to. But you would need to do the limit as x approaches 5/3 from the negative side and the limit as x approaches 5/3 from the positive side. Okay, so you would need to investigate that separately. Okay, next we're going to look at radical expressions. The best advice I can give you for radical expressions, these are expressions containing square roots, is that we turn them into rational expressions and then use those same rules we just talked about. So multiply by a fraction containing the conjugate of the radical expression, then apply those rational function rules. It's the best advice I can give you. So let me show you an example of that. Okay, in example 5, it says to compute the limit as x approaches positive infinity of this value. So notice this is a really hard thing to figure out. If I put in a positive infinity, like what does that even mean? So what I'm going to do is I'm going to multiply by the conjugate radical, which means that I copy everything the same, except I change this to a plus. Now, you're not just allowed to multiply by anything you want. The only value you're allowed to multiply is 1. So remember, it has to be a fraction that's equal to 1. So let's take a look at my work for that. So what I did is I took my original expression, put it over 1, and then I multiplied by this conjugate radical. Notice I just changed this to a plus sign. And this is equal to 1 because it's over itself. Now, when I multiply the top part, this x squared plus 1 just comes out of the square root. I write a minus sign, and then I square the x. Okay, and notice if you were to combine this, you would just get 1 on the top. Now, for the bottom, you get 1 times this expression, which is this. And now we check with our exponents. The denominator has the greater power on its x. Okay, so because the denominator is greater, this limit is actually going to equal 0. Okay, so this equals 0. And the reason that that is, if you really think about this, As x approaches infinity, this whole thing is going to get really, really big on the bottom. When you do 1 divided by a really, really big number, it's going to get closer and closer to 0. So like if you do 1 over 100, it's like 0.01. 1 over 1,000 is 0.001. 1 over a million, you're going to get more zeros. It's getting closer and closer and closer to 0. Okay, so my limit here is 0. Okay, so that's it for this video. Don't forget to watch the next video where we talk about more ways to evaluate limits at infinity.